Hey everybody, I just wanted to talk for a minute about LD50. Now this is a bit of a weird measurement. It is lethal dose to 50% of the population. So what this means is you get 100 mice together and you start force feeding them some chemical compound. Maybe it's a food, maybe it's blue dye like we did in our lab today. And you keep force feeding them this blue dye until the first one dies, and then the second one, and you keep going until 50 of them die. And that is where the lethal dose to 50% of the population is. It's an approximate measurement of whether you're going to die from eating a certain amount of stuff or not. And it's got these weird units. It's given in milligrams per kilogram. And this is one of those weird things that comes up in chemistry where when it gives you the lethal dose, the LD50, in milligrams per kilogram, it assumes you know that that means milligrams of material per kilogram of body mass. And the reason we normalize it to this idea of body mass is because it takes a different amount to kill a mouse than it does to kill an elephant. You got a bigger creature, it takes more. So it's normalized to body mass. And notice this lethality is not the same as toxicity. It's not talking about what kind of other problems it may cause. It's just saying it kills you. So one of the fun things to think about is the fact that everything has a lethal dose. Sugar is a perfect example, right? Sugar has an LD50. It's a pretty large number. It's 29,700 milligrams per kilogram. This was measured by feeding rats sugar. The thing that's interesting here is the bigger numbers are actually safer, right? In the case of sugar, 29,700 milligrams, you have to eat that much sugar for every kilogram of body mass in order to hit the LD50. If it was some other material, you might have to eat a much, much smaller amount to hit that lethal dose. So, for example, blue dye has a lethal dose of 300 milligrams per kilogram when we're feeding it to mice. It's a much smaller number, so that means it's actually quite a bit more dangerous. But we tend to have a lot less blue dye in our lives than we have sugar. And if we wanted to look at something else, caffeine. 140 milligrams per kilogram body mass. So caffeine, out of these three possibilities, sugar, blue dye, caffeine, this is the makings of a Monster energy drink, that's blue. This would be, caffeine looks like the most dangerous. But then the side question we have to ask is, how much caffeine do you actually get for each time you consume something? And again, this is lethality. One of the things that's missing here is the fact that your body has a filtration system. Your body's constantly removing these materials from your bloodstream and making it so you can't hit this lethal amount. So let's go ahead and do a calculation. I drink coffee. Every cup of coffee I drink has 95 milligrams of caffeine in it. It's 140 milligrams per kilogram of body mass to get to the lethal dose. How much coffee do I need to drink to hit the lethal dose? Go ahead, do some unit analysis, get started with it. I'll do it for you in just a moment, but give it a shot. So one of the things I like to do when I'm first working on these problems is I like to explicitly write out those extra units that are implied in it. Right? When we look at this, it says 140 milligrams per kilogram. That's just what it tells us. But when I do the problem, I like to specifically write down 140 milligrams of caffeine per 1 kilogram of body mass. Now, for somebody that weighs 75.2 kilograms, punch that into our calculators. That would be the amount we need to consume. We'd have to consume 10,528 milligrams of caffeine to reach the LD50. So the question we might ask is, how many cups of coffee do I need to drink? Now, in the problem, it tells me I've got 95 milligrams of caffeine per 1 cup. And when I look at my unit analysis, if I want to figure out how many cups I'm going to drink, I'm going to flip this over. So 1 cup is 95 milligrams caffeine. Then if I multiply by how much caffeine it takes to get to my LD50, I should be able to calculate how many cups of coffee it's going to take. And notice, this should make some logical sense. Each cup has 95 milligrams. So if I drink 1 cup, I've got 95 milligrams. Second cup, I'm going to have 190 milligrams. A third cup, and I'm going to have 285 milligrams. I've got to figure out how many cups to hit 10,528 milligrams. So I take that 10,528, divide by the 95, and I'm going to get 110 cups of coffee. Again, in my lifetime, I've probably drank more than 110 cups of coffee. However, I probably haven't drank 110 cups of coffee in an hour. We can apply this same type of logic to our blue dye problem with Gatorade. Now, we have to be careful. Notice this worked out nicely because I had units of milligrams, I had units of milligrams, so everything worked out well. Pay attention to your units. For your problem with blue dye and Gatorade, you have to take a couple steps. Unfortunately, LabPal is there to help you out. First, you have to find the concentration of blue dye in Gatorade. We're using our standard curve to do this. We get our concentration. Second, you have to get your milligrams of blue dye per a serving. So we use our idea of concentration, our total volume. That will get us to a number of moles, and then a molecular weight. Now, one of the things people have a lot of trouble with is finding the molecular weight of blue dye. It's given in the opening information of the lab. So scroll up to the top of the lab and you'll see the molecular weight of blue dye is given there. After you have that number of grams of blue dye or milligrams of blue dye in a single serving, then you can go ahead and figure out how many servings it should take to hit the lethal dose for the blue dye. Now, Gatorade's a relatively safe thing, so you should expect to see a pretty large number.